This is a lecture on area in 2 dimensions and determinants and how they're related. It's going to be mainly a development of the ideas, and it's going to be different from what you'd see in most books, but it gets to the same endpoint. And I'll do a couple of examples, but it's not focused on calculation. The question is, how do we calculate the area of a parallelogram using coordinates and vectors? So the picture here is we've got axes, and we've got a parallelogram, and for convenience, let's focus. For convenience, we're mostly going to have the parallelogram have one corner at the origin. And then if you put two vectors coming out of that, they naturally form a parallelogram. And in fact, that's something one often does with vectors. In fact, when you add vectors, you're definitely supposed to do that. And so this is a copy of A up here, this is a copy of B over here. And big A is going to be the area of that parallelogram. So if I'm given the coordinates or the components of those vectors, so some numerical information like A is A1 A2 and B is B1 B2, then I want to know how from those four numbers we're going to be able to calculate that. Okay, so let's go over here. So we have A equals A1 A2, B equals B1 B2, and let's bold that in just to make it look like a vector. Okay, and I want to get the area of the parallelogram. And we're going to call that A. So before I just plop down a formula, let's figure out some things we could figure out easily and geometrically about the area. We would like, well, we need really, we will reject any formula that doesn't satisfy the two things I'm going to say here, which are, one is that the area should be proportional to how big A is. So that's, of course, the magnitude of that vector A. And to the magnitude of the vector B. Okay. And so, for example, if we double the size of A, if we double the length of this vector A, scoot it out to here, that's going to double the size of the parallelogram. If we doubled vector B, that's going to double the size. So we need that. And we also need that A, let's look at what happens, for example. Let's scooch in a little picture right in here. What if we actually had this being A and B was equal to A? What's the area of that? Think for a second what the area of that should be. Well, that should be 0. And so when A equals B, or even when, let's say they were just in the same direction, then you'd still get a collapsed parallelogram with no height. And so that's even when B equals, let's say, some real number times A. Remember that the algebraic version of vectors being parallel is that one is a scalar multiple of the other. So that's going to be absolutely necessary. Those kinds of things are going to be necessary. So we're going to be able to check the formula I'm going to give you based on that. So what we do, the bookkeeping, there's a really important bookkeeping step, is we create a matrix with the 4 pieces of data. A1, A2 is the first row, B1, B2 is the second row. Turns out we could put them in as column vectors as well. That's a pretty surprising thing, really, that it doesn't matter. But we're going to put them in as rows. Okay. And what we're going to do is we're going to create what's called the determinant of this matrix. And I'm going to give you two notations for that. One is you just put det in front of this matrix. Another notation is we actually just rewrite the matrix and we change to single vertical bars around it. I'll show you why, a couple reasons why I don't like that notation. One reason I don't like that notation is it doesn't make clear the huge difference between the matrix itself up here and the determinant of that matrix. The matrix has 4 different numbers. It's a lot of data. It's all the data of these 2 vectors together. It's all the data of the parallelogram. It's got shape information. This is actually just a number derived from those 4 numbers, and I'll give you the formula in a second. It's not just a new version of the matrix, but the notation looks like it's just a new version of the matrix. And here's the formula. And often in my classes, I go ahead and we really go more depth in this, and we figure out why right from the start. We figure this out for ourselves, why this must be the right formula. But I'll just give it to you. It's the product of the diagonal entries minus the product of the off-diagonal entries. But then we want to make sure that that actually has at least some of the properties that we want here. So let's check. Oops. Let's go ahead and okay. Let's check the properties. So that first property was that I wanted it proportional to the magnitude of A or magnitude of B. Well, let's look at this. Okay, the formula here, if I have, it's A1 times something minus A2 times something. So let's see. If I double both A1 and A2, then certainly I'm going to double this whole answer. Okay. And this similarly for B1 and B2. So for as an explicit numerical example, we could say like the determinant of, let's say this is 4, 2, minus 1, 3. That's going to be 4 times 3 minus 2 times minus 1. So that's 12 plus 2 is 14. Whereas if I doubled A to 84, that's just going to be doubling each of these terms, and I'm going to get 28. Okay, so that shows something. Let's look at the picture for that. Let me do a new version of the picture. So here we have our axes. 4, 2, 1, 2, 3, 4, 1, 2. So there's our A vector. And minus 1, 3. That goes to the left 1 and up here. So it's like this. Looks almost like a right angle, but it's not quite. If I just didn't draw it very carefully. And here's the parallelogram they make. Oh, didn't make it look very parallel. Okay. And the claim is that the area of that is 14. And if I doubled A to 8, 4, it's going to be twice as big. The whole thing together is 28. So far this is looking promising. Okay. Now, what about our other property? Let's look at the determinant of A1, A2, and let's just do the simple case first. If it's A1, A2 again, I take the same vector twice and make a collapsed parallelogram. Well, that's certainly going to be 0, because it's A1, A2 from the diagonals minus A2, A1, and so that's 0. And a little more complicated is, suppose I had, this is RA1, and this is RA2, so that the B was just some real number, a scalar times R, that is, times A. then it's just going to be A1 A2 from the diagonals minus, it's the same thing, it's just in a different order, but that doesn't matter here. And you get 0. So remember, this is really, really crucial that this is going to happen, that I should get a 0 area when I put in the same vectors or even scalar multiple vectors. And notice that that means that this minus sign, which is in some ways the weirdest part of the formula, this minus sign absolutely has to be here. This kind of looks a little bit like the formula for a dot product, which would have a plus, and then these guys wouldn't be mixed. It would be A1 B1 plus A2 B2. So it's similar, but the switching is different and the minus sign is very, very different. But this tells us this minus sign has to be here. There's no way we could get automatic zeros coming out of a formula in such general cases without the minus sign doing that. But, and it's really important to realize that, because the minus sign also tells us something that's rather disturbing. The minus sign means that we can get a negative. And the order matters. So for example, let's go back to this example. I'll be able to copy a lot of this. Suppose I have -1, 3, and 4, 2. So it's the same geometrical example, except now this is put in the first slot and this is put in the second slot. Now that's just going to switch things around. I'm going to have 2 times -1 and then minus 4 times 3, and now it's going to be -14. So we can get negative answers, but wait, I thought this was supposed to be an area. Oops. And the order we put the vectors in matters. And so a fancy way to say that is that if I look at the determinant, let's go back up even further. Let's look at the determinant here, copy it back down. The determinant of this, if I switch the A and the B, so I turn this into B's and these into A's, then it becomes a negative. Whoa, darn. Okay. Well, it turns out that's okay. And there's really no way around it. We couldn't have a nice formula here because we need the negative for it to vanish in the right cases, and there's no way around it. It's going to give us a negative. So it turns out that really the determinant doesn't really calculate just the area. It calculates what's called the oriented area of the parallelogram. Okay. And so the oriented area, let me put that in italics here. This is positive. Let's look at the rule. I'll just tell you the rule, and we can see that in a few examples. It's positive when, if I go from A to B, remember here in the positive example, this was A, this was B. That's kind of an inscrutable A, isn't it? You can sort of see it. It's positive when rotating from A to B is counterclockwise. That's the positive direction of rotation in mathematics. And so when you rotate from vector A to vector B, and that's counterclockwise, you get a positive answer, and it's negative when that rotation is clockwise. So for example, when I switched the A and B here, when this became A and this became B in this example here, then that's when I got a negative answer. So B to A, the rotation, let me draw that here, is clockwise. That's the negative direction mathematically. Okay, so that's a little surprising. The good news, of course, that the absolute value of the determinant of a 2x2 matrix, okay, that really is just the area. Because we could just strip off that minus sign. Who cares? It gave us a minus sign, but we can just ignore it if we want to. There's a lot of cases where we don't ignore it. And so this is actually a nice case where the mathematics, the algebra, is telling us, hey, here's some extra information that it's easy to get at. And it's also easy to ignore if you want. You can just strip off the minus off of this, not a problem. But in a lot of cases, it actually is very significant. One thing that's annoying about notation if you use the vertical bars, the vertical bar notation for the determinant, remember this notation, which you see very commonly. It's pretty annoying here, though, because now suddenly you want to take like vertical bars, the inner vertical bars mean the determinant, but that can be negative even though it looks like absolute value bars, and then the absolute value bars really are absolute value bars. Okay, this is just bad. And that's why I tend to use the det notation, because it avoids confusion with absolute values. Okay, and there will be cases where we don't use the absolute values. There will be cases when we do, and it can be a little weird. Okay, so let's just do a few more quick examples. The determinant, the absolute most basic example. I did one random example for you, but one absolute basic example you'd better have is if you have 1, 0, and 0, 1 as your vectors. What does that correspond to in the picture? Those are I and j. And this matrix is the identity matrix. So if you're familiar with that, that should be something that you know is important. And of course, the area should be 1. And of course it is. It's 1 times 1 minus 0. Whoops. Equals 1. But what about the determinant? What if I switch the rows? Well, we saw already that, as I've said, the order matters. I have exactly the same picture, but now instead of this being the first one and this being the second one, what if I switch that? This is the first, the vertical is first, and the horizontal is second. Then I don't get 1, I get a minus 1. And that's because of this orientation thing. For a rectangle, along the axes, oops, then that's going to be, let's look at the determinant of that. Well, let's say that's like A and B. So let's do that here. If this were, let's stretch it out. I'll just rewrite it. Try and make this big so it doesn't get small on YouTube. What if that's A and B, and they're not slanted yet, so it's not a fully general parallelogram, but if those are just A to the right and B up, of course we know what the answer should be. That should be AB. And exactly that's what the formula gives you, AB minus 0. So a lot of evidence that this is giving us the right answer. Let me give you a really, really good piece of evidence that this is the right answer. I'm not going to take you all the way to the most complicated link between the algebra and the geometry. Or let's say, not example, let's say a more complicated type. What we'll do is we'll shear. We'll do what's called shearing this guy. We'll leave the base the same, and we're just going to change the parallelogram in a way that doesn't change its area and doesn't change its height, but changes it out of a rectangle. What we're going to do is we're going to take this vector b and we're just going to shear it over, which does different from rotating. We're going to leave it at the same height, and it's going to go over here. And then, of course, this has got to go over as well. So here's the new parallelogram. And notice it's got the same height. B is still, oops, is still the same, is still the height of the parallelogram. But now this vector here is like, let's see, what do I want to call this? Let's say this is like x comma b. And the interesting thing is that x doesn't matter. One way to picture this is to picture a stack of books sideways, and like here's the layers of the books, and just push the books over. You're not inflating the books or compressing the books, you're just moving them around. The volume of the books is the same, and if you look at them end on, you've still got the same cross-sectional area. And of course we know that because the way the standard formula for the area of a parallelogram is base times height. And that's still a times b. So we should get still a times b for the area, and that's exactly what happens, because what's going on now, we just have to modify this example a little bit. We're almost done with this part of the story. the base is still the vector a comma 0. Now this is like x comma b, this slanted vector, which has the same height. That's still ab. The determinant of that is still ab, because you just get minus 0x, and that's just ab. And so that's really, really good evidence this is what's going on. And in fact, it's really the big reason why this is the correct formula. If you go through a more careful derivation of this from scratch, that the reason this the diagonal minus anti-diagonal version, the reason that calculation works to give area is exactly because it gives the right behavior under shears. Again, one notational thing. Oops, just kidding. Often you'll see this. If we call our components A, B, C, D, I've been trying to be a little more systematic about like A sub 1 and A sub 2, that kind of thing. This is what people often memorize, AD minus BC. It's exactly the same thing. Diagonals minus the anti-diagonals. Okay, so that's an introduction to sort of the why of the determinant and why it connects to area.